Okay, this is part two. It's the experimental evidence. Um, yeah, this was a big question. Every time I start looking at data, I always ask myself, where do I begin? Actually, start anywhere. Anywhere when you don't know, somewhere is better than nowhere. So where do I begin is a good question, but don't wait for an exact answer. And I put this in all my presentations simply because when I was researching a paper, I think in finance or statistics, I cannot remember, this was about a year back, I found this paper on a journal site and they showed me the first 2 pages. If I wanted the rest of the paper, I had to pay for it. So I was Googling some more and I found this link on ResearchGate. And so I said, hey, that's an opportunity to get some papers free. So I clicked on it and I found exactly the same paper. Same outline, same style, same wording. And then I looked at the name. What's a different name? I said, oh my God, is this what's happening in academia? So when you find a paper, please investigate. Is that person the original author of that paper, or was it somebody else? Interstellar travel versus interplanetary travel. Gravity modification will give us interplanetary travel. Light takes between 30 minutes to an hour to get to Mars. And so if we can do that kind of travel that fast, we can answer the question, let's do our lunch on Mars. But interstellar travel, that's a totally different issue. Because the reason why gravity modification cannot get us interstellar travel is because it's still bound by Lorentz Fitzgerald and Newtonian gravitational transformations. So you cannot use gravity modification to do interstellar travel. But at least it'll get us interplanetary travel and we can build a commercial interplanetary civilization while we prepare to do interstellar travel. And why is this the case? Because probabilities are not bound by these transformations and their time invariant. So we can say, I'm here now, in the next instant, I'm over there. So that is why I say that we have to understand probabilities. We have to ask the questions, how does nature implement probabilities? And how do we control probabilities? I've put forward a few papers on how photon probabilities can be controlled using electric fields. And when I saw Jeremiah's magnetic field experiment where the photon was deflecting, I said, hey, that's it. We have to dig into that much deeper. And that's one of the reasons I would like to talk to him, because yes, we can do experiments to prove. Why engineer? This is Robert Goddard, 1926, March 16th, practically 95 years ago. As a society, we have to ask ourselves the question, do we want to take another 95 years to get to interstellar travel? No. My internal goal is 2040. There are two other reasons why engineering is important, because we use engineering to prove that a hypothesis is correct. And we use engineering to prove not just that hypothesis is correct, but it is valuable. But a more important and more in the background reason for why engineering is correct, is necessary, is because we need to use engineering to develop design principles so that we do not spend 300 or 400 experiments like I did in 2000, trying to figure out what's going on. If I could do 5 experiments and know what was going on and say, this, that would have been great. But no, I had to spend that years reproducing my experiments 300 to 400 times before I finally said, hey, I'm not getting anywhere. I'm a little bit stubborn in that sense. Maybe a little bit slow. And if necessary, we can look at an engine and see how we can reverse engineer it and then learn from it. So what's the purpose of an engine? This lady shows us with her facial expressions that yes, there is an important reason for a purpose for an engine. It is to provide a means to arrive at a destination. The whole point of travel is to arrive at a destination. It's not about velocity, it's not about power, it's not about energy, it's about arriving at a destination. And therefore, two important things are important: vectoring and modulation. Vectoring is telling us where to go, which direction to point our rocket set or our ARPs or gravity modifying engines, which direction to point at. And the second important is modulation. How soon or how late do we want to get to that point? And with that, attenuation and amplification comes accepted that there is energy in the picture, but we don't want to talk about how we use the energy to define how we arrive at a destination. Then we can include probabilities as part of the process of the purpose of arriving at a destination. The experimental evidence. Okay. Okay, I'll get to this first. Okay, this is the new equivalence. Nonlinear transformations and linear transformations give identical results. And you can show that with numerical modeling. You get the heavenly bodies in our solar system, and we can use a classical method, and we get the escape velocity. You convert that escape velocity into time dilation, and take that time dilation and plug it into Lorentz Fitzgerald transformation, and hey and behold, we get the exact same equations. The margin of error is trivial. You cannot show this. You cannot prove this. At least I do not know how to prove this analytically, but you can prove it numerically. You have to build the models, look at the numbers. In photon shielding, there are 3 different equations with regard to photon shielding, and they all give, within a certain operating range, they all give identical results. So the question now is, which is the correct equation? Here we see that there is an equivalence. Nature, behind all this, there's something that's going on that makes linear motion and nonlinear motion equivalent. Gravity is an I field, and we see, if you look at the orbital velocities which are tangential to the mass, you can see that the Nye field has an acceleration in this downward direction. And I won't get into that because I've already explained a little bit more, quite a bit of this in the previous slides. So we know, first, gravity is an I field. Second, oh yeah, this portion. These are the equations I used to model. I used analytical equations that are constructed for the model of distortion in a gravitational field, and therefore you can get the center of mass. And there's a function here, y, which determines the distribution of the mass. And I found out through the difficult way, I found out that this equation is not integrable. So I had to use numerical modeling to solve it. I had a friend who was a much better mathematician than me. This was when I was living in Colorado, who tried to break it up. She comes from a family of mathematicians, and it couldn't be broken up. It couldn't be simplified. And then later, a reviewer came back and told me, this equation is not integrable. So I'm happy. So you can see that this is the classical method, and this is the G is equal to tau C squared method. of calculating that, and the errors are parts per million. It's trivial. And the Y function, I told myself it's not enough to just model a sphere. What happens is particles are not really spherical in shape. In some of my later work, I showed that particles have different structures, and so are they still valid under different structures? I used about 10 different distribution of masses, and I still came back with G is equal to tau c squared. So I'm satisfied. I'm happy. Somebody with better mathematical skills than I wants to go ahead and prove this analytically, which cannot be done. Go ahead. Okay, now mechanical motion. You take a string, tie a ball to it, and you rotate it. So this is the pivot here, this is the string, and you have the greater the radius, the greater the velocity, the lower the radius, the lower the velocity. So you have a knife field here. And the acceleration of the ball is away from the pivot. And what is holding it together is the tension in the string. And then we have some physicists come along and said centripetal forces don't exist. What? Centrifugal forces don't exist. What? What do you mean centrifugal forces don't exist? There must be equal and opposite reaction. There are two forces. One is the ball trying to run away from the pivot. The other is a string holding the ball back to the pivot. So when somebody tells you that centrifugal forces don't exist because it's outward motion, it's not correct. The knife field structure tells you that it is an outward motion. It is the tension in the string, the centripetal forces that prevents the ball from flying out of control. So there are a lot of these sort of mistakes in physics. So you have to be very, very, very picky when you read something. So I used some random number generators, generated different angular velocities, different radiuses, and I found out using the classical method, these are the numbers of the acceleration, and these are numbers using the knife field method, and the error is trivial. So G is equal to tau c squared works in gravitational fields and works with mechanical forces. So I was cheek enough to ask the question, does Lathwaite big wheel experiment work? See, what Lathwaite did was he took a 50-pound wheel, spun it to 3,000 RPM, and then he did this over his head. It was practically weightless. And you'll see lots of videos of people deriding Lathwaite's experiments. Is that what they teach us in university? To deride other people's experiments, to deride anomalies? No, anomalies are there. They are red flags telling you, hey, there's something going on. You need to investigate. Hello, I'm here. Don't ignore it. Look at the anomalies. They have something to tell us. So I built a model, numerical model. I had to model the X and Y velocities on the disk and the X and Y and Z velocities on the rod. And these are the RPMs he used. I actually watched the video and timed everything to see what was going on, so that I wanted to get as close as possible to what Lathwaite was doing. And then I built a model, and then I used a regression to summarize the data, and you get this equation. Acceleration is spin times rotation times multiplied by the square root of the hypotenuse, this hypotenuse. And a scientist who doesn't ask questions will tell you, hey, that equation's wrong because the units are wrong. No, if you ask the question, how do I get it? It's a regression. There is a coefficient of regression that is 1, which has the units of square root of meters, which makes the equation correct. So sometimes it's a little bit annoying when people say, hey, no, you're wrong, without asking questions. Ask questions and then tell me, come to a conclusion, tell me I'm wrong. So this is the model results of the acceleration across the disk, that rotating, spinning disk. And I looked at it and I said, oh no, this is going to go to zero. So many 1,000 data points. I bet you it's going to go to zero. It turns out that the average of all those 1,000 points is never zero. It is some value that obeys the formula I just showed you. What happens is that the disk is observing an acceleration that is orthogonal. So the force, so this is spinning this way, the rod is rotating this way. The force is orthogonal to the spin and the rotation, and it's upwards or downwards, okay? And whether it's upwards or downwards depends on the sense of the spin. If they are, when you're looking at it, if the sense is the same, then they are towards you, if I remember correctly, if I recall correctly. If they are different, then the sense is away from you. And the model results shows that the average acceleration is as a certain value determined by the equation, but the wheel itself experiences tremendous stresses due to the difference from the average acceleration. And then 2018, I went to Madrid. That's the only time I've been out of this country in the last 21, 22 years, because I see no interest in leaving, going out and seeing what's going on there outside, in the outside world. I met this guy, Gabriel Barcelo Rico Aveo. He's with Advanced Dynamics, his own company. And he was presenting at this workshop conference, and I was presenting a paper on photon probabilities and the properties of photon probabilities and randomness and that sort of things. And he had a demonstration. He solved Lathwaite's big wheel experiments by using sophisticated mathematical theory. He had not, until I talked to him, he had not heard of Lathwaite or his experiments. So the non-English speaking world has their own research that's going on that in a lot of ways is more advanced than what is going on in the English speaking world, because the English speaking world, they tend to deride anomalies. And I have no clue why that happens. So what he did was he demonstrated a rudderless model submarine at the Madrid Naval Academy that was turning. And you can look up this YouTube video. It's around minute 5 where you actually see the submarine turning. No rudder. And then in his presentation, he opened up and showed he showed diagrammatically what was in his model submarine. It was Lathwaite's big whale experiment. There it was. And I said, here, I don't have to do the experiments anymore. This guy has already done it for me without even knowing anything about Lathwaite. So now let's look at electromagnetism. You have a nice furry ball, that's an electron, and this is the plane of the knife field. And the knife field is created by the mechanical motion of the electron upwards with the magnetic field going into the slide. And by left-hand rule, you have a velocity on this side that is parallel to the mechanical motion. And on this side, you have electromagnetic velocity that is anti-parallel to the mechanical velocity. And so therefore we get a gradient of spatial velocities, an I field with an acceleration that's going in this way. And so when you look at the calculations, again, this is all based on random number generators, you find that this is the acceleration using the classical method, and this is the acceleration that's using the knife field method. and the errors are trivial. So knife fields and G is equal to tau C squared works for gravity, mechanical forces, and electromagnetic forces. But note here, the key thing here is you have two sources of velocities, the mechanical and the electromagnetic. That becomes key to developing rotation-based gravity-modifying devices. Deconstructing particle enough. I read both his papers. It took me a year to read both his papers, and that's all I did. I didn't do anything else. Just read his papers. Read, reread, reread, reread. I wanted to understand what he had focused on and what he had not focused on. He pretty well clearly documented his work much more than most people do. And so I was able to figure out that he had shown there was weight gain and weight loss, but his focus was on weight loss. And the reason why his experiments are important is because they will show us whether it is mass or matter that causes gravitational fields. So the basic essence of his bilayer disk, the top part is superconducting and the bottom part is not. And if you spin something 20-something centimeters across, the acceleration here, the G forces are 98 Gs, and the mass is 0.95 kilograms. I got it from an email from him maybe about 10 years ago. And so you get 98 Gs at the edge. It's going to break up, obviously. Didn't any of the researchers who tried to reproduce this experiment do that simple basic calculation and say, hey, we have to do something about the 98 Gs? No. So he observed weight loss, the inner radius that's around here, the inner radius was between 0.1% and 0.25%, and the outer radius here was between 0.3% and 0. I cannot read that, 0.5%, I think, weight loss. So that tells you that there's a radial effect. And what is that radial effect too? That's a question that needs to be answered. Now let's step back a bit. If it was a pure superconducting disk that was not bilayered, then we'll see that an asymmetric field will have net canceling effect. So the force field of the magnetic force field will have a force in that direction, will be cancelled by the opposing symmetrical field that has a force in the opposite direction. And similarly, the bottom layer will cancel the top, and this bottom will cancel this bottom, and this bottom will cancel that top. So it's net cancelling. So with the symmetrical field, you cannot see anything. Also, the side downward forces on the side will be cancelled by the upward forces in the center. So the fields are symmetrical, they're net cancelling. So, but if you put in a bilayer, a second layer, for example, this bottom layer, as particle enough have done, what we see is that magnetic field is now asymmetrical because the bottom layer magnetic field has been trapped by this bottom layer of this superconducting disk. So we have a net effect. So in effect, we should see some net forces here and some net forces here, which particle enough states that when the disk is stationary, it does observe a force. But he missed the electric field. That's why many times when people try to reproduce his experiments, they didn't get any results. Firstly, because of the G's that cracks the disk. Secondly, because they didn't convert the superconducting field into an asymmetric field. And from this, I arrived at the conclusion, I published this around 2011, 2012. You do not need the superconducting magnetic field. All you need is the magnetic field. It goes back to the three-step schema. The source of the field, and the effect. So we don't care about what the source is. We just need the field because we want to investigate the effect. So I built a model. All my models are in Excel. To do it correctly, you need an Excel add-in called X numbers, because Excel will only calculate to 15 significant digits. With X numbers, you can go to 250 significant digits for acceleration, gravitational acceleration. That means 249 decimal places. Now I'm told that X numbers has been revamped, and X numbers will let you do calculations up to 4,000 significant digits. So that's something to think about. You don't have to do Python code to run your own, build your own models to do that. It's available in Excel. So when I build a model, I'm assuming superconducting fields are flat, essentially flat. And you do get this small weight loss at the center and big weight loss at the edge. And so there's this tangential property here that there's this radial property here that increases as the radius increases, the weight loss increases. And then if you mess up your magnetic field, let me go back to this. So where the lesson here is where you measure the weight loss makes a lot of difference to what you will observe. So you don't want to measure the weight loss here. You want to measure the weight loss at the edge of the spinning disk, if that's possible. Okay, so when you mess up the magnetic field, you can get things like this: weight loss, huge weight loss here at the edge, and substantial amount of weight gain in the middle of the disk. And so these cancel out and you get null results or you get weak results. So you have to be careful about how you construct the magnetic field, because you can get false negatives. In diseases, because I've written a paper on diseases based on my data modeling experience, the problem with diseases is the false positives. Here, the problem here is the false negatives. Okay, now if we look at the model of a stationary disk without electric field, we do see this. There's a weight loss at the edge, and then some weight gain in the center of the disk. So asymmetric fields is what we require to do gravity modification. Portal said that it's also it has a shielding effect. That means if you tilt the disk, the weight loss is you don't get a situation when you tilt the disk, there's no weight loss. You get this type of situation that even when you tilt the disk, you get some weight loss because it's a shielding effect that shields the gravitational field above you. Whereas if it was a vector effect, then when you tilt the disk away, you should lose the weight loss. Comparisons. Okay, how am I doing for time? Comparisons. This is based on my experiment. The results were from March 2000. This is one of the few results I still have, which I documented. This is a circuit that does not have any moving parts in it. So as we increase the voltage, the current, the weight drops. In this example, when we switch off the current, the weight does increase and return to normal, but it takes a longer time. So there's a latent effect in there. And whatever theory that's developed to explain this needs to explain that sort of behavior. But it's not always that. I've seen 90% weight loss for about 30 seconds and then complete regain of the weight. So the phenomena is not simple or straightforward. It's a little bit complicated. But what surprised me was the next slide, also from one of the March experiments, is that you have current down here, you have voltage up here, you have linear resistance, and then suddenly it's gone. No matter how much current you apply, the voltage is the same. I have not been able to reproduce this, and I'm so grateful that I actually recorded this. But this is the reason why I do not believe that Cooper pairs are the source of superconductivity. I think quantum theory cannot distinguish the two. I believe, and I may be completely wrong, but this is what I'm thinking out aloud so that you guys can hear it and go investigate. I believe it is superconductivity that creates Cooper pairs, not the other way around. Okay, Paul Murat and John Brandenburg. Most of you know these people. I met them first in 2009 at a specific conference, and he put together an energy box, which is basically the Searle effect generator, and they observed 7% weight loss. But the thing I really appreciate what these two guys did, because I'm a visual thinker, I need to see pictures, I need to see videos in my mind. That's what they did. For me, that was the most important thing. They showed me the direction of the electric field in green, the direction of the magnetic field in blue, and the direction of the pointing vector. Pointing vector is basically an energy vector. And so from this, you can, at least I can say a few things, but we'll get into it in a minute. So from my interpretation of Portland's work, that is what is primarily important. It's the left-hand rule, E, B, and V. And the V, the gradient of V velocity is what is the knife field, which causes the acceleration effect. And in their example, they have equivalent. Instead of the V, they have the S, the pointing vector. So, end of part 2, we know how knife fields are implemented, and they are universal. They describe all macro forces. The reason why I say only macro forces, not all forces, because I do not have a fundamental idea of what's going on in the nucleus. What binding energy tells me is that the space-time, and this is sacrilege. Everything I've said is sacrilege according to the current physics scope. So why not add more sacrilege? The binding energy in a nucleus alters the space-time of nucleus. So the space-time of nucleus is different from the space-time outside the nucleus. That's why I cannot say whether G is equal to tau C squared is still valid inside the nucleus. So, in this presentation, you have seen how we have distilled the various important properties to figure out how to do force generation. And that's me when I used to shave my head. And let's go to part 3.